Yes. You sure can. Okay, so we're looking at a mass on an incline that's being pulled up, yes? Yeah, so the question is, you have a mass on an incline with friction. I can't remember, were there homework problems like this and you're pulling it with a rope maybe parallel to the incline, so, and I don't, there's lots of different ways to phrase this. You could be given the tension in the rope and maybe it's accelerating up the plane, or maybe you're not given the tension in the rope, but you're told it's pulled at constant velocity when you figure out what the tension is in the rope by balancing forces, right? Some of the force X components equal 0, some of the force Y components equal 0. But it kind of depends on how it's phrased. The question was, how do you calculate works associated with this? Well, you have to be given some indication of how far it moves, some delta X that it goes up the plane. And that would be a natural thing to be given in this problem. And oh, I'm sorry, I know you guys can click on it, but I want to unshare the screen so it'll be on the video here. So if you knew the tension and you knew delta X, hey, that's easy because I just use the work done. And I'm not sure if you're talking about net work or just the work done by the tension. Oh, okay, network. Well, so what would you say to this? Suppose I gave you this setup and I said, I'm not going to tell you what the tension is, but it's moving up at constant velocity. So it's moving up at constant velocity. And it moves from, past X equals 0. And then later on, it moves past X equals 2 meters. So this is 2 meters. Just moving up and it passes those 2 points. How much net work is done on the block between those 2 times? That's an easy question. Why? Yeah. Well, because acceleration is 0, and so, but okay, so elaborate on that a little bit. Oh, okay. Yes, Amelia? Yes, we have this great theorem, which was our first of several work energy theorems, but I call it the work kinetic energy theorem. That says the net work done on a particle-like object, right? It's not rotating, it's not compressing, there's no springy forces or anything in your system. That's equal to the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. Well, in this case, if it's moving at constant velocity, the final and the initial velocities are the same. And so the right-hand side is 0. And so the net work that's done is 0. Now, net work means, of course, the tension's doing positive work, but gravity's trying to pull it in the other direction. So gravity's doing negative work. If there's friction, friction's doing negative work. The normal force is doing 0 work. So there are lots of things. But one thing that's easy to know is that when you add them all up, they're going to add to 0. And that may or may not help you get the work done by tension or the work done by friction. But, suppose you move it 2 meters and you want to know how much work is done by friction in those 2 meters. So just to outline the general procedure without doing the problem, because I haven't even put angles in here or anything. But the free body diagram for this would look like, well, I've got a weight force. I've got a tension force going maybe parallel to the plane. I've got a normal force perpendicular to the plane. And if I'm pulling it up the plane, then I have a kinetic friction force going back down the plane. And, maybe I want to calculate just the work done by the friction force. Now, the first thing I might want to decide, just to make sure I don't forget about it later on, is what's the sign of the work done by friction during this 2 meter climb up the plane? It's definitely going to be negative, so it doesn't hurt to put that minus sign there just to remind me in case I end up calculating the magnitude of the work or something like that, just so I don't forget it later on. All right, so now what I need is the magnitude of the friction force, right? So the general formula we're going to use is calculate the x component of the work times delta x. And we said for that simplified formula, we have to align our x-axis with the direction it's being displaced. And so in this case, fx is negative, and that's what's going to give us that minus sign, right? It's a negative x component of this force, if that's plus. So I'm presuming we're given the kinetic coefficient of friction, so then we've reduced it. If I could only find the normal force, my calculation would be minus mu k times the normal force times the delta x, and I'm presuming we're, I'm just kind of half making up a problem. Presumably we're given those, but we aren't given the normal force. So then how would I get the normal force in this case? Yes. Right, and again, how it's going to go kind of depends on what we're given for the tension force. If we're given the tension force, then that's just a known force, and I can do exactly what you said. So let's presume we're given the tension force. Another kind of situation that comes up is they say it's moving at constant velocity, but I'm not going to tell you the tension. And then you have to figure out just the right tension that would cause it to move at constant velocity, maybe. But in any case, if I want the normal force, it seems like I want to use F net equals ma along this direction, right? So I might say I've already chosen x along that direction. Let's take y to be perpendicular. And if I did the sum of the force y components equals may, let's assume we're given the tension force, but it may be accelerating, right? Maybe somebody's pulling too hard and it's speeding up, or maybe they're not pulling hard enough and it's slowing down as it goes further up the plane. Who knows? Sum of the force y components, 0 y component, 0 y component. This is all along y, so I get a plus Fn. And then this is more or less in the negative y direction, right? We have to be given an angle here, 30 degrees. If that angle is 30 degrees, many of you are getting used to just writing in that angle there is 30 degrees. So it looks like if I want the y component of this, I'm looking at this side of the right triangle, which is mg cosine 30 with a minus sign. Okay, what's ay in this case? It might be accelerating, right? It's 0, because if it's accelerating all along x, not along y. So that would allow me to solve for f. I mean, it's hard to tell. This could go a lot of different ways depending on what you're given, but that's the kind of thing you might do. All right, good warm-up problem there. Again, if anybody wants to stay after and talk about a problem or two, that's fine with me too. I know on Friday I spent way too much time sort of talking about stuff, and so our goal for today is problem solving. We're going to use these formulas that we worked so hard to derive. So where we were before Friday was we had the work kinetic energy theorem, which only applies to a rigid non-rotating object. Okay. Then we allowed for a much more general kind of system, a system where we might have multiple parts to the object connected by springy forces. Sometimes the springs are invisible, like if I say my system is this eraser plus Earth, and there's an invisible spring that I'm stretching and it's contracting now when it pulls it back down, right? Springy forces like that. And for those kind of systems, when we're going to talk about, there's a little bit of a, I pulled the wool over your eyes, and maybe some of you know why, but we'll go back and talk about what was a little bit suspicious about the derivation. But for right now, let's not worry about it. We said the network, we're interested in just the work done by external forces, because often we're not in control of internal forces. It's like if you have a jar of molecules, you don't know much about what's happening with internal forces, but I can control the forces of the edge of the jar as I compress it on the molecule. So that's kind of the motivation there. And so the network done by only external forces, we have to be very careful about defining what our system is now the change in kinetic energy plus the change in potential energy, where the potential energy is a function that depends on the internal forces for the system we've defined. And we were told if your system consists of an object close to the surface of Earth plus Earth, and gravity is an internal force, then the associated potential energy function is mgy, where plus y has to be up from Earth. If you have objects connected by a spring, and we call the location of an object x equals 0 when the spring is completely relaxed, not compressed, not extended, then the potential energy stored in the spring is 1/2 kx squared. So if x is negative, that means it's compressed. If x is positive, it means it's stretched. But either way, you're storing potential energy in the spring as you compress it or as you stretch it out, because you can get kinetic energy out of it either way if you compressed it or extended it. And then finally, if we have some, planet-sized things like Earth and Moon or something like that, or maybe an astronaut who's really far away from Earth or something like that, we have a more general potential energy function associated with gravity. This one's only true if one of the objects is really close to the surface of Earth, whereas this one is true even if you're really far away from Earth or 2 Earth radii above the surface of Earth or something like that. And that one's a little bit weird because it has this minus sign. We just have to be really careful keeping that minus sign in place. Okay, and we talked about all this stuff and examples at the end of last time. I thought I put that in. Oh, here's where I thought I was. Okay, yes. So, and we talked about springs, spring forces. We're not so concerned about the spring force, but rather the potential energy. And remember, if you've got a mass attached to a spring, you just mark some point on the mass. And when the spring is relaxed, we're going to call that point's location x equals 0. Positive x's are stretched, negative x's are compressed springs. And there's a spring constant k that's associated with it. Okay, let's do some practice now. And I want to do so let me pass out a worksheet. I believe for those of you on Zoom that this is posted for Friday's class. At the top of the worksheet, it says conservation of mechanical energy, although it's probably an old title for this because it's not all about conservation of mechanical energy. But let's do the first one together just to kind of warm up to it. We're going back to a problem that we could have solved with kinematics. A 1/2 kilogram ball is launched upward at 30 meters per second. And we're supposed to ignore air resistance. And we want to take gravity to be an internal force, just to practice with our new formulae. We could have, done the work energy theorem, a work kinetic energy theorem with this, but we are going to take everything of relevance in this problem and put it in the system. So let me show the board here. And just like I always want you to draw a free body diagram and axes on it when you use Fnet equals ma. When you're using energy methods, I always want you to define what your system is. Now, in this case, I've told you that I want your system to be everything. That sounds a little bit extreme, but what I mean is all the items of importance in this problem. What's important? Not only the ball, of course, but Earth, because Earth is what's pulling on the ball and slowing it down. So I'm going to throw the ball and Earth in my system and make the gravitational force between them be an internal force, associated with which there's going to be a potential energy function. Okay, so this means ball plus Earth and gravity is an internal force. Okay. Now, if there were some other forces acting, like a hand reaching in and pushing on the ball while it's flying up, then we might call that external force. But you just got to be very clear. So in this case, there aren't any other forces because we're told air resistance is negligible. So that's pretty much it. Find the maximum height above launch point that the ball reaches using energy methods. So I'm going to take initial to be just after release. And final to be the maximum height position. right? At which I know it's momentarily come to rest. That means our final kinetic energy is going to be 0. That's what we're going to use for that. Okay. So let's write down our work energy relation that's valid for springy systems. And my system is certainly springy. The ball and the earth have a springy force between them. So our work energy relation says the net work done, we're only going to calculate it due to external forces, is equal to the change in the kinetic energy of the system plus the change in the potential energy of the system. Okay, and I'm just going to expand out both sides of this. What do you say about the net work done on my system, ball plus earth, where gravity is internal, as it moves from its initial, just after I've released it, to the final maximum height position? How much work is done by external forces? Well, that's the great thing about putting everything in your system is there aren't any external forces, right? When I say everything, I mean everything that matters, and any force that matters, I'm going to put in the system. So in this case, there's nothing left to be an external force. If it did, that wouldn't be everything. We should have included it here. So the net work done by external forces, the only other force that might have acted is air resistance, and we were told to ignore air resistance. It's not a big enough force, so it's not doing much work, presumably. Okay, how about the change in kinetic energy? Oh, that's me. I just go into brainless mode here. 1/2 mv final squared minus 1/2 mv initial squared. I don't really have to think much about it. We'll think at the next step. Plus the change in potential energy. Now, in my system, I have one internal force, and it's gravity. It's gravity between an object that's close to the surface of Earth and Earth. And that the associated gravitational potential energy that we're supposed to use is mgy for that case. We only have 3 cases, so if we know how to use them all, we're good. And we always have to take up. We use that in the derivation of this potential energy function. So it's important that plus y is up in this particular case. Okay, so I would write that as mgy final minus mgy initial. Where plus y is going up from Earth. And at this point you go, wait, what were they asking for again? Find the maximum height above the launch point that the ball reaches using energy methods. Okay, so what is it that I want to find here in this problem? Y final or Y final minus Y initial. Notice, I could say I'm going to choose my coordinate system so that right after I release it, that's where Y equals 0 is. That would be my Y initial equals 0. Or if you don't want to do that, we could just say, let's factor out the mg, and I have Y final minus Y initial here. And this is our variable that we want to solve for, if you like, how far it went up between initial and final. Okay, what do I know about V final here? It's 0 because my final is when it momentarily comes to rest at the highest position. So let's throw that piece away. And I think we're given the mass of the ball here, 0.5 kilogram. V initial is 30 in SI units. Technically, I have a factor of m in every thing here, so I could really divide out the m too, but I'll just leave it in for now. You could cancel the m's. Minus 1/2, m is 0.5 in SI units. V initial is 30 in SI units, so that's my minus 1/2 mv initial squared. Plus m is 0.5 times 9.8. 0.5 times 9.8 times Y final minus Y initial. And then I just want to solve for Y final minus Y initial. Okay, and so I'm going to get 1/2 times 0.5 times 30 squared divided by 0.5 divided by 9.8. And that tells me that Y final minus Y initial is equal to 45.9 meters. That's pretty high up there. you might question whether air resistance is negligible. It depends on the kind of ball you're throwing, you know, how dense it is. Okay, I'm going to set you loose on C, but I want us to think together about B. We knew how to solve this problem before using kinematics, right? This is the kind of stuff we did a lot in chapter 2. Constant acceleration kinematics at the end under the influence of gravity for one-dimensional motion. So how if I were just going to go back and say, let's just check that we get the same answer and let's solve this with kinematics over here. Can anybody suggest one of the 3 kinematics equations that might get us most directly to how high it went up between initial and final? Dylan?
Would it be V final squared equals V initial squared plus 2A delta Y?
Yeah, so I always like to put, you know, in this problem, there's only one dimension, but, you know, I really like to put those coordinates on there because a lot of times it's moving in Y and X and we don't want to forget and mix them up. Plus 2AY delta Y. Now, why did you choose this one and not one of the other 2? What was your thinking there?
We don't have time. We're not asked to solve.
Right. We don't have, that's often our reasoning with this. We don't know time and we don't want to know time. So let's throw away the 2 that have to do with time. That's not always true, but in this problem, that's true. Okay, and then we just substitute in. We say Vy final is 0. Vy initial is equal to 30. Ay, in this case, if we're taking plus y is up, is minus 9.8 times delta y. And delta y is the same thing as y final minus y initial. If you look at this and you know, solve for this, you'll see you're writing down actually the exact same thing, right? The 1/2 mv squared, it's hidden in here, right? I could have multiplied every term by m and then divided by 2, and I would have had a 1/2 mv squared sitting there. So it's really the same thing, just kind of rearranged. We're not doing anything different. You get delta y equals 45.9 meters again. Okay, any questions on that? Yes.
I know it's upcoming thing that's going to be on like the work unit, like on final, like the question when
Probably on the next exam, I would be likely to tell you if it's a problem that you could do either way. Please use energy methods. As I said in A, using energy methods, right? And so you're going to do C now, and it says calculate something using energy methods. That means not kinematics. So, but that's a good question. If it's ever unclear, feel free to ask. If I really don't specify, I'm not going to hold it against you if you do it any way that's correct. But feel like it's probably likely that I'm going to force you to do the more recent stuff. So try C. C is another problem we could have done using kinematics, ignoring air resistance. Find the speed that the ball has after it has risen 30 meters. Notice it goes up 45.9. So it's not to the highest point at that point yet. Still moving up after it's risen 30 meters. What's its speed then? See if you can calculate that. But using this new piece of machinery here, this work energy theorem. It's not the work kinetic energy theorem, but it's a different kind of work energy theorem. Same system I'm recommending. Okay, most of you are still diligently working, but I'm just gonna kind of show what we do. It's the same equation we're starting with in this case. Again, if we're taking the same system, there aren't any external forces left that would be important to do work. So their net work must be 0. Air resistance would be the only one we're told to ignore. And again, here I can be kind of brainless mode, 1/2 mv final squared minus 1/2 mv initial squared plus mg y final. I'm just going to factor out the mg like I did before. And I think, to make my life easier here, I can see, look, I've got a common factor of m, so let's divide both sides by m. That makes all the m's go away on that side, and 0 divided by m, it doesn't care, it's still 0, right? It doesn't matter what m you divide it by, it's still 0. So the m's go away, that's kind of nice. And what are we after? We want to know if the initial speed is 30, I think it was the same initial state, right? We want to know the final speed when this distance is, well, I really like 30 in this problem, 30 meters up, so everything's 30. So the idea is y final minus y initial is 30 in SI units. V initial is also 30, I believe, in this problem. And we just solve for V final, and you get V final is 17.7 meters per second. Could have done that, again, with kinematics. We also could have done this problem. Well, let me ask first, any questions about this or alternative methods people might be thinking of? Yes. Because by and I should actually say, I didn't use the same initial and final. My initial was the same in my work down here. My final was wherever it is after it's risen 30 meters. But this is what I chose for part A. And so by definition, my final was when it reaches that maximum height, momentarily comes to rest. If it comes to rest, that means V final is 0. So you got to be very careful, at least keeping in your mind, but I suggest even writing it down. What, in words, how would you describe what final and initial is? Because otherwise, sometimes in a complicated problem, you might change your mind halfway through, and that's going to mess everything up. I was going to say also, this ball is behaving like a particle during its motion. So I could have used the work kinetic energy theorem. That wouldn't be for the same system, right? This system is not a particle-like system that I've defined up here. But I could have solved this problem also. And I know students don't always like more choices, but in energy, there's often a lot depends on your choice of the system. Suppose I just said the system is just the ball. It's a particle. Okay, we're told that we can do our good old friend now, the work kinetic energy theorem. Okay, and let's go back to part A just to be definite, right? So in part A, for my initial and final, the final is kinetic energy of the ball is 0. The initial kinetic energy of the ball is easy to calculate, right? This is still our 30 meters per second that we're going to square, and the mass is the same. Now I can't ignore this W net over here, because it's the work done on the ball, that's my system, by all forces, and gravity is certainly a non-negligible force. So how much work is done by gravity in this case? Well, first of all, is it positive, negative, or 0 as the ball goes from initial to final highest point? It's negative, right? So air resistance, we're presuming that does a negligible amount of work. That would also be negative if it were important. The only important force that is doing work on the ball is the gravitational force. And it's doing negative work, right? As the ball is rising, it's pulling down on the ball, so it's slowing it down. So this is going to be negative. And then I can calculate the work done by gravity using Fx delta x, right? If delta x is up, Fx is negative, and the magnitude of Fx is mg, right? And how far it moves up is what we wrote before as y final minus y initial. Hey, that looks That's the same as the equation we wrote down before, except it's here with a minus sign on the left-hand side instead of being with a plus sign on the right-hand side. So we're writing down the same thing in either way. It just feels very different when you define your system differently, but you see we're doing the same algebra here in all, or at least getting the same equivalent equation in this case. So oftentimes you'll have choices about how you do this. Sometimes some choices are better than others. In this case, I would say they're all about the same. We did about the same work every single way. But as things get more complicated, they might be a better choice of system. Other questions on that before we go to the next problem, which I just kind of want to set up and talk about the system that might be wise to choose for this one. This is a little bit more complicated. An ice cube is, I didn't choose this location very well. An ice cube is, you know, that's supposed to suggest that friction is kind of negligible because the ice is really slippery. It's rolling down a hemispherical bowl, or not rolling, sliding. Okay. So I'm going to draw a cross section of this hemispherical bowl. We're told of the bowl that it has a radius of 20 centimeters. So this distance is 20 centimeters, or if I want to use SI units, 0.2 meters, right? And we're going to release it from rest up here. It's supposed to be a tiny little ice cube. Rest, that's my initial. Maybe I'll put an I next to it to remind me. There's my initial, and we want to know what is its speed as it passes the bottom of the bowl. So here's my final position, at which point it's zooming to the right. We want to know the speed at that point. That's clearly going to come out of our 1/2 mv final squared, right? Now, I've got to think about applying choosing a system. You know, I might say, let's try our new piece of machinery. The net work done only by external forces is equal to delta KE plus delta PE. And I've got to define what my system means so that I know what external means and what internal means. Now, since we have, again, gravity is an important force acting on this ice cube that's going to cause it to speed up, essentially. And we've got a convenient potential energy function associated with gravity, right? We'll see how to use that. So it seems to make sense that I would want to make gravity internal, or at least that doesn't seem unreasonable. So I'm going to take my system to be the ice cube plus Earth. And just to be definite, gravity is internal. But there's another force that might be doing work here, and that is the normal force. We're assuming friction is negligible. Doesn't say it here, but it's suggesting that there's very little friction here because it's a melting ice cube. But the normal force is pushing on it. And there might be a question about whether you should put the normal force in your system or outside your system, right? I mean, I could think of, hey, this thing's trying to, you know, interact with the Earth, but some external force is getting in the way and pushing on it, always in that perpendicular direction. I'm going to suggest here, it doesn't really matter which one, but it might be a little bit confusing if we put it in the system because we don't have a potential energy function associated with a normal force. That's not one of the three we talked about. So let's leave it external. So I'm just to be definite, I'm going to say the normal force is external. And we'll see that no problem. That's going to make it so that we don't have to think too much about it. Okay, let's expand both sides of this. The net work done by all external forces. Well, we only have to look at the parts of the system that are moving. That's why I don't have to worry about the Earth when something's falling or rising from Earth, because Earth isn't doing any moving, and so there's no work that's done on Earth. But the parts of the system that's moving here is the ice cube, and gravity is an important force. That's going to come in here. But the normal force is also an important force. It's external, so the work done by the normal force belongs on this side. What do you say about how to calculate that? as the ice cube is sliding down, is the normal force doing positive or negative work? It's not doing any work. I mean, that was a trick question. I didn't give you the third option, but it's just, you remember we talked about someone in outer space with a string, right? And they had a little mass on it and they were, rotating it around in a circle. And we were saying, how much work does it do in a half revolution? Well, it's not doing any work on it. Each little step it moves in this direction, the force is pulling on it in a perpendicular direction. So it's doing a little bit of no work, a little bit of no work, a little bit of no work, a little bit of no work. Same thing here, a little bit of no work because the normal force looks like that. When it goes from here to here, it's doing a little bit of no work because the velocity is in, its displacement is in that direction and the normal force is in that direction. So anytime a force is always perpendicular to the local direction of motion, it's not doing any work. And that's what the normal force is doing here. So the only force that could have, the only external force that could have done work was the normal force. It's the only other force besides gravity that we're told about. That is external and it's doing zero work. Anybody want to clarify that, or is that clear enough? You might have been worried when it was external here, but then you quickly see, oh yeah, normal force is always going to be zero. So don't worry about making it external. It's easy to put a zero on that side. Okay, brainless mode, 1/2 mv final squared minus 1. This is the kind of stuff you love on an exam because it sort of calms you down. I don't have to really think and be creative. Plus mg y final minus y initial. Again, oftentimes you'll find it's convenient to factor out that mg factor. Okay, and well, I'm going to let you solve the rest of this. Okay, we've set it up here. See if you can figure out what to substitute in so that we can solve for v final. Okay, so there's only one thing to think about, and that is what is y final minus y initial. We'll talk about that in a second, but the same nice thing, this won't always happen, but in this case, again, there's a common factor of m. So just to save myself some calculator work, I'm going to divide both sides by m, and 0 divided by m is still 0. So that's good. The m just disappeared. Apparently, the answer doesn't depend on m, right? It's going to have the same speed no matter what the mass of the ice cube is. All right. V initial is 0. I'm hoping that's not released from rest at the upper edge of the rim. And it's V final we're after. So I just need to substitute in here. I know little g. What should I substitute in for y final minus y initial? Yeah. Well, let's think about this. We're using mg y final minus mg y initial. So we're using the formula potential energy associated with gravity when one of the objects is near the surface of Earth is mgy, where we always have to take plus y up from Earth. Okay, so if you like, plus y, I could draw it like that. Plus y is up like that. What's the sign of y final minus y initial? It's negative because it's going down to a lower y, if plus y is up, right? And we have to choose plus y is up. We're going to use mgy. It's negative. And what is the magnitude of the change in the y coordinates? It's not, as was suggested, this arc length, I think, right? Or this diagonal length. It's neither of those things. How far do we go down in y? It should be the radius, right? I go down, I started up at here, at this level, and I went down by 1 radius. I went down by 0.2 meters, so minus 0.2 in SI units. And the final answer is not too interesting. I get 1.98 meters per second. But the minus sign is all important. If you don't put that minus sign in there, you're going to be taking the square root of a negative number, which most people just throw out the minus sign, don't worry about it. But it should be giving an indication that something is wrong there. All right, good. Any more questions on that one? Before we try out another. I don't have any, I'm surprised I don't have a spring one in here, but you will, in lab this week, you're going to be doing a lot of practice. There's an experiment part, and then there's some practice problems. I thought that was good just because we have the exam coming up next week, and I want you to practice with the energy stuff, just like we did with gravity. But let's use that third potential energy function associated with 2 gravitationally attracting objects that are really far apart, not near the surface of Earth, but like Earth and Moon, or Earth and a space shuttle that's really far away from Earth, something like that. That is, for example, like question 3A. A 30-kilogram rock is released from rest 1 moon radius above moon's surface. So that means it's 2 moon radii from the center of the moon is where we've released it, right? And the reason I chose the moon is because we're going to let it drop all the way to the surface. The moon doesn't have an atmosphere, so we don't have to worry about air resistance messing things up, making things hard to calculate. Okay, so the question is, what is its speed just before striking the surface of the moon? And I'm going to use this gravitational potential energy function that works when we're talking about objects that aren't, one of them isn't near the surface of Earth. In other words, and it looked like this: minus our good old friend capital G, 6.67 times 10 to the minus 11, times the product of the 2 masses, just like we had before. But instead of dividing by r squared, we divide just by r. Okay? And since I have a nice gravitational potential energy function, I'm going to take gravity to be an internal force. So my system's going to be the rock plus moon. Gravity's internal. There's nothing else to be external, so that's going to be a 0 on the left-hand side of this relationship. The net work done by external forces is equal to delta KE plus delta PE. Okay, just to be definite, system is rock plus moon. Gravity is internal. Getting kind of sketchy up there, but you get the idea. And that's nice. There aren't any other forces on the rock. There's no air resistance, no atmosphere on the moon. And so that's a nice 0. And now brainless mode. I like this. 1/2 mv final squared minus 1/2 mv initial squared plus, ooh, now I can't quite be so brainless because I've got a new potential energy function. So I need let me write it up here. We need PE final minus PE initial. And it's kind of a mess. So we're just going to write it out very carefully. Okay. Let's put PE final. Now, PE final has its own minus sign that comes with it. That's what we have to be careful about. It's easy to lose a minus sign. So just to make sure I do it right, I'm going to put these things in parentheses. And what goes in this parentheses has its own minus sign that goes with it. Minus G, I'll say Big M is the mass of the moon. Little m is the mass of the rock, just so I don't have to put subscripts on there, right? It is, sorry, I thought I heard somebody asking a question. Divided by R, and we want the final R. How would you describe the final R that we should use here? It's at the surface of the moon. Well, I didn't write down what initial and final is, but it's hardly any choice here. Initial is when you release it from rest. Final is when it's just about to hit the moon. What R should I use when it's just about to hit the moon? The radius of the moon, because we're always measuring to the center of some big sphere of mass. So I'm just going to put R moon there. Minus, and again, this potential energy function has its own minus sign that goes with it. G times the mass of the moon times the mass of the rock divided by, what's the initial R that I should be substituting in there? 2 times the radius of the moon, right? That's just from the verbal description. 2 R moon. Okay, and now, oh gosh, our M's cancel out again, right? There's a factor of little m, the mass of the rock, in every one of these things, and then the 0 doesn't care if I divide it out, so I don't want to put that in my calculator over and over again. And I'm after, let's see, V initial is 0. I'm after V final. It might be worthwhile for us to simplify this a little bit, because G, capital G, is kind of a painful number. So is the mass of the moon. So is the radius of the moon. And if I just do it like this in my calculator, I'm going to put them in twice. And it's worth doing a tiny bit of algebra here. First of all, minus minus is plus. Let me just do that, right? I could say plus, and let's get rid of that minus sign there. Minus minus is plus. So this one has a plus sign. This one has a minus sign. Now, let's just think of this thing here as a thing. I've got minus one of those things plus 1/2 of those things. If you have minus one of those things plus 1/2 of those things, how would you sum up how much we have overall? Minus 1/2, right? Minus one of these plus 1/2 of these gives minus 1/2 of those. So this all simplifies down to minus G times the mass of the moon divided by 2R moon. I mean, that was worth that mental effort because I don't have to type all those stupid scientific, numbers into my calculator over and over again. But, make sure you show your work, because if you mess it up, I don't want to take off, tons of credit on the exam because you just missed some weird algebraic step. So I got to plug those numbers in, right? And then take the square root at the end to solve for V final. And in this case, not surprisingly, you get a fairly big V final. V final I have as 2,400 meters per second. I'm sorry, I'm looking at the wrong one. 1,700 meters per second. 2,400 is the answer for part B. Do we have time for part B? Oh, we have time to at least discuss it. Any questions on this one here? It's no more conceptually complicated. It's just a little bit messy because of all that scientific notation stuff. So here's a different problem, but the same kind of setup. Same rock is launched directly upward from the moon's surface. And we want to know the escape speed for the launch. Maybe you read about this in Giancoli. I don't know if he talks about it, but maybe not actually. That means, what is the smallest launch speed the rock could have and never fall back? So imagine you're on the Earth. You got this rock, right? No air resistance. I throw it up with a wimpy throw. It goes up and it comes back down, right? Now, if I have a super cannon and I give it a huge speed going up, what's going to happen is it's just going to keep going and going, right? The moon pulls back on it for a while, but eventually it gets so far away from the moon that it just keeps going and going. So it's 1,000,000 miles away and it's still going at 100 miles an hour. That wasn't the minimum speed I could blast it off with. I could have done a little bit less because it had some leftover kinetic energy at the end. The minimum speed is going to correspond to this, right? If I throw it up and it keeps getting farther and farther and farther away, but as it gets farther and farther away, its velocity or its speed gets smaller and smaller and smaller and smaller. So it actually makes it as far away as you like. But the farther away it gets, the closer its speed gets to zero. In other words, it doesn't get off to infinity with some leftover 30 meters per second of speed. It has zero leftover speed, even though it gets infinitely far away. It can never stop, because as soon as it stops, it's all over. It's going to fall back. That gravitational force doesn't cut off anywhere. So I know we don't have time to solve it, but let's just set up. Again, I'm going to take my system to be the same. Rock plus moon, gravity internal. Let's just describe what my initial state is going to be. Just after launch, that's easy. Oops, launch. The final is the tricky one to describe. Final is going to be very far away. Very far away means I can essentially plug in R final is infinity. That's okay. R final is infinity. It's going to be in the denominator. When you divide by a really large number, you get something that goes to zero. So that's easy. That's going to make your life easier. Very far away with no leftover speed. Oh, that's good. Oops, speed. That means V final is equal to zero. So the final state is really far away with no leftover speed. And you can imagine plugging that in here, right? This would be our R final here, and this would be our R initial. Right? PE final, PE initial. R final is going to be infinity, so this term is going to go to zero. R initial is going to be our moon, because that's where we blasted it off from, 1 moon radius away from the center of that big sphere. And we're just going to find out V final will be zero. We want it to have no leftover kinetic energy when it's really far away. And we're after that V initial that corresponds to V final equals zero. So a little bit of arithmetic to do there, but I won't do it for you. The answer, if you're working it out, is 2,400 meters per second in that case. All right, good. You'll see some examples in lab having to do with the spring force. Professor Lockett's class might be confused because I don't think they talked about the spring potential energy, but that's okay. It'll be good practice for us. And as always, I guess I should mention, last week we did a bunch of problems in lab. I posted solutions on my website. I know Dr. Falco might have emailed them to you, but I put my own solutions up just because sometimes she doesn't draw all the free body diagrams. I want to make sure you see those free body diagrams. I'll do the same thing this week. So I'm going to post my solutions on our website so you can refer to those, for the exam that's coming up next week.